Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present solid epoxy coatings, powder coatings. Powder coatings epoxy systems are 100% solid epoxy formulation which contains no solvent or water. These systems are applied as aerosols, composed of the finest distributions of powder particles in air. Powder coatings applied by the fluid bed sintering processes were introduced in the 1950s, whereas in the 1960s electrostatic spray application was also introduced. High molecular weight, usually over 1,000 epoxy resins, hardeners, and other additives such as flow control agents, pigments, fillers, and catalysts are often used in their formulations. Their solid nature and the absence of solvent in these formulations significantly reduce the pollution potential and fire and explosive hazard in the coating plants. In addition, in these applications, as the unused powder can be readily recycled, the wastage is minimal and they have the highest transfer efficiency compared to other types of painting coating techniques. The powder coating systems are adequately flexible and chemically resistant and exhibit excellent adhesion on metallic substrate. These systems are also confer very good corrosion protection to metallic surfaces. However, powder coatings are not weatherable, and in these conditions they become yellow and exhibit matting and chalking. Powder coatings therefore often used exclusively for interior applications, for example for machine parts, metal furniture, domestic appliances, and for electrical installations. Powder formulations are often produced mainly in melt processes based on fusion bonding and dry blending techniques. High temperature often employed in dry blending techniques, therefore formulations with reactive hardener must be avoided. A heated kneader or an extruder is used to homogeneously wet the components and mix items to produce a relatively high viscosity melt. If liquid components have to be used in the formulations, they cannot be added directly. Instead, they are premixed with small proportions of the resins in melt and then crushed into particles, which are then added to the mixer. After passing through rolls and cooling belts, slabs are formed which are crushed and ground effectively in special mills. This process requires resins with relatively high softening temperatures and glass temperatures above 50 centigrade to avoid fusing during the milling. These factors make the resins to be hard and also restrict the choice of resins to be formulated for powder coatings. Therefore, after processing, the proper curatives must be employed to reach a good balance between flexibility and hardness. Anyhow, after the milling, superfine components and coarse particles are separated using cyclones and by screening to produce a powder with a narrow particle size distribution for uniform film. However, the effective surface energy is much higher in finer particles. If the particles are too fine, there is a risk to agglomeration, which is called the caking effect. Agglomeration leads in leveling defects in the film, and that's one reason for the separation of these particles during the process. These particles may also restrict the minimum film thickness for the powder coating. A minimum thickness of 55 micrometer is required to reach a smooth and glassy film in automotive powder clear coats. Also, the preparation of layers of up to 600 micrometer thick is possible with using this technique, while there is no risk of blistering and sagging in these coatings. In the powder coating processes, the film formation occurs through the melt process, and the melt viscosity is quite low at the start of the stowing process, which is the best condition to achieve the optimum leveling in the coated film. That's why a resin with a high Tg and a lower average molecular mass is more suitable for powder coating. The combination of a high Tg and a low molecular mass in the resin results in high melting temperatures and lower melt viscosities. Fluid bed sintering has been recommended to replace dipping process applications. In this process, powders are employed in a fluid bed tank and no solvents are involved. The tank has porous metal sinter plate bottom where compressed air fed into the system and agitate the powder particles to form an aerosol. For coating application, the objects are initially heated to temperatures above the melting temperature of the powder coating, and then it is submerged in the tank. Upon contact, the particles melt and form a film at the surface of the object. The temperature and the heat capacity of the object, the melting temperature and the particle sizes of the powder, and the dipping duration control and determine the thickness and the quality of the obtained films. To complete the process, the object is then placed in a stove where the film formation is completed. Therefore, only heat-resistant objects with limited sizes are suitable in this process. Thicknesses in range of 80 to 400 micrometer can be reached by fluid bed sintering powder coating. Electrostatic spraying is another method for powder coating application. In this process, the powder is fluidized by compressed air and transported to the spray gun, in which the particles of the aerosols are charged electrostatically. The powder is then sprayed onto the object, which is electrically conducting in earth. The transport of the particles to the object and their adhesion to it happens through the presence of the electrostatic charging. Two methods employed for charging the powder particles including corona charging and tribocharging. In corona charging, ionization is employed to charge the powder particles, whereas in the kinetic or tribocharging, the particles are charged by passing through tubes of special materials. The charged powder particles deposited on the surface of the object with the aid of an electrical field. The filming is then finalized by stowing the object. Thicknesses in range of 400 to 150 micrometer can be reached by electrostatic spraying powder coating. Electrostatic power spraying has good throwing power. Although the primary transfer efficiency is low, for example 50% due to the Faraday effect, the oversprayed power can readily be recycled in the cabins. Recycling results in 95% overall transfer efficiency, which is the highest between the suitable paint systems. In this process, the contamination of the powder in the cabins has to be kind of prohibited, because as it is happened, there is no way to clean the powder again. Moreover, considerable effort is required when the paint color is changed, as the complete cleaning of the powder spraying booth is quite hard. High molar mass, for example 1500 to 3000 gram per mole bisphenol A epoxy resins, are ideal for use in powder coating. Glass transition temperature of these resins could be in range of 50 to 65, whereas their softening temperature could be in range of 80 to 100 centigrades. However, solid bisphenol F and Novolog type epoxy resins can also be used for powder coating. For cross-linking, often di-C and derivatives, polyphenols and polyanhydrides are employed. For powder coating applications, fine powder di-C has to be mixed with the composition. Catalysts also have to be incorporated, as di-C is less reactive than other amines. Some commercial acrylated di-C products are also available. However, its derivatives are more reactive. Powder coatings containing di-C can be cured at 185 to 220 centigrade for 15 to 30 minutes, whereas accelerated di-C and its derivative need 10 to 15 minutes at 150 to 118. During the cross-linking, the NH group of these curatives reacts with the oxygen rings of epoxy resins by the addition reaction. Dic contains 5 H atoms attached to different N atoms, but its effective cross-linking functionality is lower. However, Dic catalyzes the self-cross-linking reactivity of epoxy resins in a way, and therefore less than calculated stoichiometric amount of Dic is often required for cross-linking. Practically 97 to 3 or 95 to 5 ratio of epoxy resins and Dic are always used. Phenolic crosslinkers are polyphenols or phenolic adducts of bisphenol A resins in which the chain ends bear phenolic hydroxyl groups instead of oxygen rings. Novalogs are also phenolic substitutes for cross-linking epoxy resins. However, phenolic groups of all these components are not active enough, and therefore cross-linking of epoxy resins with these curatives requires relatively high temperature or catalysts such as amidazoles. For curing, the powders containing these curatives can be stored for 10 to 20 minutes at 130 to 160 centigrades. The self-cross-linking of the epoxy resins can also be promoted by catalysts, and therefore, here again, less than stoichiometric amounts of phenolic crosslinker is required for curing. The third class of curative used in powder coating epoxies are anhydride. The curing here starts by the formation of esters with the secondary hydroxyl groups of the epoxy resins and opening the anhydride rings. Results in carboxyl groups subsequently react with the epoxy rings. Pyromellitic dianhydride, combinations of pyromellitic dianhydride and trimellitic anhydride and trimellitic diol are the most preferred curatives of this type. Amines and amidamines, for example, phenyl 2-phenyl imidazoline, can be employed as catalysts in these systems. Here again, less than the stoichiometric amount of anhydride is added to the system. Two generic formulation examples of epoxy powder coating system cured by Dic and phenolic crosslinkers have been presented here. Epoxy-polyester hybrid system are of common powder coating formulation and consist of epoxy resins and saturated polyesters which contain aromatic polycarboxylic acid and polyols with short aliphatic chains. Both resins must have glass transition temperature of more than 50 centigrade. The amount of polyester and epoxy resins required for these hybrid systems is calculated based on the acid number or AN of the polyester and the epoxy equivalent weight or EEW of the epoxy resins, and it is in range of 70 to 13 or 50 to 50. In this hybrid system, as the secondary hydroxyl groups also participate in the cross-linking by reaction with epoxy groups, excess epoxy resins, for example, more than the stoichiometric amount, can be used. The cross-linking mechanism has been depicted here, and the esterification catalyst can be phosphine, phosphonium salts, tertiary amines, and organic salt of heavy metals. Temperature between 140 and 200 centigrades are employed for stoving in hybrid system, and the preferred application method is electrostatic spraying. These systems provide a balanced property profile, more flexible, harder, and more weatherable, which makes them suitable for exterior coating applications. However, the level of corrosion protection and chemical resistance is not as outstanding as that of pure epoxy powder coatings. A typical formulation of these systems have been provided here. If polyester cross-linked with hardeners that have much lower EEW values than the employed epoxy resins, if polyesters cross-linked with the hardeners that have much lower EEW values than the employed epoxy resins, for example, triglycidyl isocyanurate or TGIC with EW of 100 to 108 gram per equivalent, the polyester is the main resin, and these formulations are referred to as polyester powder coatings. These systems are water resistant, exhibit good balance of hardness and flexibility, good chemical resistance, and show low tendency for yellowing. However, TGAC is toxic, and currently new alternatives such as glycidyl esters of aromatic polycarboxylic acids are often employed. These curatives are comparably less reactive, but almost similar film properties can be reached. Epoxy acrylate system has been introduced in other videos. Solid epoxy acrylates are mixed with the crosslinkers, pigments, and additives and can be used for powder coating applications. High molecular polycarboxylic acid and linear polyanhydrides can be used as crosslinker in these systems. The polyanhydride first react with hydroxyl groups to form carboxylic groupsome, which are consequently react with the epoxy groups to form beta-hydroxy esters. These esters can again react with the residual anhydrides. The cross-linking has been shown here. These systems require a low temperature of 114 to 160 centigrade for stoving and are suitable for automotive original equipment manufacturing or OEM coatings, and especially as clear coats, in which the higher temperatures may adversely affect the other layers of the automotive coating system. Aliphatic or cycloaliphatic polyanhydride cured epoxy acrylate coatings exhibit excellent weather resistance, high gloss, and hardness with the relatively good yellowing stability, features required for weatherable top coats, for example, for automotive or OEM clear coats. I hope you found this video interesting, and thanks for your attention. Please share your comments, thoughts, or questions, and I will come back to you soon. Thank you.